Hello and welcome everyone, this is What the Math, and today we're going to be finishing the terraforming adventure we've had with almost every major body in the solar system. This time is going to be Neptune. Beautiful, beautiful Neptune, 8th planet from the Sun, and really the last planet. Pluto is no longer a planet since 2006, so we're going to consider it as a planetary object that will be discussed later on. But today we're going to be talking about Neptune. I'm going to show you, or basically I'm going to talk about some of the facts about this planet and to discuss some of its moons as well. Let's start with a little bit of history actually, and also just the general features of Neptune. So this is actually just Neptune, there's nothing else, there's no sun here, so some of the numbers here might not be exactly correct. But what is it? Well, it's a gas giant, but specifically it's also known as an ice giant. It's very, very similar in composition and structure to Uranus, which was the previous planet I've done terraforming of. Specifically, we actually did terraforming of its moons, not the planet itself. There is a terraforming of all of the planets video that is also available, but I'm not going to be doing this today. We're only going to be focusing on its moons to make this a little bit more realistic, because terraforming the actual gas giant is not particularly challenging, but it's also not particularly realistic at this point. So Neptune is a gas giant, like I mentioned, but it is different from Jupiter and Saturn because most of its composition, specifically if I were to show you the materials inside, most of this, like the layer right here, is actually something we call ices. This is elements like water, ammonia, I think methane is also considered to be an ice. So these are essentially like liquids that turn into ice. It is still a gas giant though, so it does have a gas gas layer right here, but the rest of it is kind of a liquidy soup. Now, what is it, name, and what is its sort of historical origin? Well, it's interesting how it was actually discovered, because we didn't discover this just by looking in a telescope. Neptune was kind of a theoretical planet that people thought about, that they had to exist because of the way Uranus was actually orbiting. The Uranus orbit is so strange that if there wasn't another really massive planet after it, it should have been more circular. But because it sort of deviated from its own pathway, and I'm talking about Uranus, the scientists in 17th and 18th century, specifically Newton and some of the other scientists, his contemporaries, realized that there must have been something else. There must be another really massive planet after it that changes Uranus's orbit. And they started thinking about it, they started trying to calculate where that planet would be, and they actually didn't realize, but they have seen it several times. Newton has seen it, Galileo has seen it. They just didn't know that it was a planet. They actually thought it was like a star or something, because it's so far away from the sun and its orbit is so slow compared to other planets. And it's also kind of it's a little bit dim, and it sort of moves in a very kind of a slow way. It's really hard to see its motion, in other words. So they didn't really realize that this was another planet, but they found it, and they found it in somewhere around 1850s. It was actually both the French and the English, and they had a bit of a conflict because of it, because they didn't know really who found it first, and then eventually they agreed that it was a mutual discovery. So it was found by both the French and the English. So they didn't have to start another war, because they did have quite a lot of wars in those times, especially England and France. Now, it's named after the god of water, Neptune. So most of the other, here I'm going to pause this for a second, most of the other planets, specifically, sorry, not planets, but moons orbiting around Neptune, are also named after either the Roman deities or their children. So almost everything here is like water people, water gods, water deities. Now, interestingly, this is actually quite a massive planet. It is a little bit smaller than Uranus, but it's more dense, and it has a very, very high gravitational field on its surface. Its surface has the second highest gravitational field in our solar system. No, sorry, I guess in terms of planets. Sun has the first, obviously. Jupiter has the second, and this would be the third, because it is very small, but it's very massive, and it's a lot more dense as well. So it has one of the highest densities of all planets, and it's very, very, very dense for a gas and for an ice giant. Now, how far is it from the sun? Let's actually switch to the other simulation. And this is a simulation where there are all of the planets and all of their moons right here. So this is Jupiter, this is Saturn, and right here is Neptune. So it's about 30 times the distance of the Earth from the Sun. So it's called astronomical units. It's about 30 AU away from the Sun. So its orbit, 1 year in other words, takes about 165 years. It's pretty long, which also means that it has really long seasons. It's about 40 years per season. And interestingly, it's actually, in the way that it's aligned to the Sun, in the way that it sort of spins, is very, very similar to Earth. It's about 24 degrees. In other words, that it has very similar seasons to the Earth, but obviously different because it's actually it's a gas giant. It has gas and liquids instead of hard surface. And don't get confused, it does have hard surface. Inside, deep inside, there's actually a solid core, approximately 1.2 times the mass of Earth, and it does have very similar composition to Earth, but this core is under like huge pressure, 100,000 atmospheres, and also about 5,000 degrees Kelvin. So it's very, very hot, very, very pressurized. So yeah, we're probably not getting there anytime soon. And the actual composition of Neptune is very similar to other gas giants, and specifically similar to Uranus. So it has some hydrogen, it has some helium, but most of it is made out of methane, ammonia, and water. So this is why it's really called an ice giant and not so much a gas giant. So these are slightly different composition from Saturn and Jupiter. And the other interesting thing about it is its color. So let's look at Uranus for a second, and then let's look at Neptune again. So where is Mr. Uranus? Uranus is right here. So look at that. Uranus, Neptune. Uranus, Neptune. That's not Neptune. This is Neptune. So they do have very similar color, but Neptune is a little bit more dark. Now the blue color is from the methane in its upper atmosphere. And the methane actually basically turns it blue. It turns both Neptune and Uranus blue, but Neptune is a little bit darker, and this is what is still a mystery. We don't really know what element causes this dark blue color instead of the light blue like the Uranus planet. So there's still a lot of unknown things about this planet, but all in all, it's actually quite awesome and quite mysterious too. And you can see right here that it's about 17.1 times the mass of Earth. It's about 3 times bigger than Earth in size. Its density is quite high for a gas giant, but about 4 times lower than Earth. And its surface temperature is pretty cold. Now, its surface temperature is minus 226 degrees Celsius, yet the temperature inside on the surface of the hard shell is something like 5,000 and maybe 6,000 degrees. Now, one of the coolest properties of its atmosphere is that as you go deeper, at least that's the theoretical theory behind it, as you go deeper, you start encountering some really crazy things. Like, for example, this liquid part here it's not like water or ocean or at all, actually. It's something that we call ionic soup. It's basically water under pressure and temperature that starts disassembling into hydrogen and oxygen, that then creates this electric field as well. And so it actually is responsible for both the magnetosphere, which basically is what Earth has as well. It protects us from the solar flares, protects us from death, in other words. And on the other hand, it creates temperature. It creates a huge temperature, and so this planet on the inside is actually hotter than Uranus, even though Uranus is closer to the Sun. Now, so there's something going on inside this Neptune planet that we are not sure exactly what, but it's basically, it's really hot on the inside. But except for that, there's also a really interesting phenomenon where a lot of the carbon actually gets converted to diamond, and so scientists kind of think that there's things like diamond rain and diamond glaciers, huge diamond mountains everywhere. So it would be a pretty interesting sight if we ever made it to the inside of this particular gas giant. But going back to the magnetosphere, its magnetosphere extends about 24 times its radius, so approximately over here. So in other words, planets, or sorry, not planets, but moons like Triton are actually covered in this magnetosphere and are protected from the solar flares. And this is great news for if we ever decide to terraform and settle on Triton. It's already protected by Neptune's magnetosphere, so we actually don't have to worry too much about the ionic radiation that would actually otherwise kill everything alive and fry everything alive on the surface of this particular moon. The other thing that is actually not shown in this game, but is a reality, is that just like other gas giants, Neptune also has it has rings. So there's actually 5 different rings around it, and let me see if I can show you where they're located. So they're, and it's probably easier to see on the other in the other simulation, which is here, Neptune and its moons. So right around here. And it's actually where these other moons are located as well. There's actually 5 asteroid rings, basically rings like Saturn, but they're much less prominent and much less visible. So those are rings orbiting around Neptune, and usually they're mostly contain ices and rock. So they're kind of like dirty snowballs. Now, interestingly, because Neptune is so far away from the Sun, it's actually very close to the region of solar system we call Kuiper Belt. This is where things like Pluto are located, but it's also where a lot of asteroids and comets are originally from. So because this planet is so massive, it actually creates a very interesting sort of like a gravitational space-time hole in here. Not a black hole, but just like a bulge that essentially pushes a lot of the asteroids around. It kind of disturbs their orbit, and Neptune is probably responsible for most of the comets that we have in our solar system, because its gravitational field most likely caused them to change their orbit and then come toward the Sun. So it does cause a lot of havoc in the Kuiper Belt. And for all we know, Neptune was also possibly responsible for the death of dinosaurs. Very likely that it caused that asteroid from the Kuiper Belt to come closer to Earth and then smack and kill the dinosaurs. Now, the only time we actually visited this planet was during the Voyager 2 journey to the outer solar system, and it passed by, took a few pictures. I'm going to show you one of them. I think it's actually the most popular picture that we actually currently have, and it's the picture right here. So this is the actual photo of Neptune and its biggest moon, Triton. So very beautiful, very mysterious, and very awesome. So one day, hopefully, we'll make it there again, and possibly even settle this beauty. So let's talk a little bit more about the moons. But actually, specifically, I wanted to mention something else before. The orbits of the moons. So if you look closely, I'm going to close this for a second. All of the moons orbit nicely counterclockwise here. If you look at Mr. Triton, Triton is a rebel. It's moving clockwise. It's moving against all other orbits, even though it's actually relatively, well, not relatively, but somewhat aligned with the other moons. Neptune actually has 14 known moons, possibly more, but there are 14 that we actually found, and a lot of the other ones are called irregular satellites. They're actually too far away. These are all captured asteroids, and they're kind of sort of in the farther regions, not as important. And then there's also a few here in the center. These are smaller rock-like formations, also asteroids, but they were most likely there from the start. And so what we think today is that Triton was most likely one of the captured objects from the Kuiper Belt. It most likely approached Neptune and then somehow got captured, and while it got captured, it very likely kicked out all of the other moons that this planet had, and they actually, because of its influence, gravitational influence, and because of the way it orbits against the flow, it very likely influenced a lot of the other bigger moons that used to be here and then kicked them out. So in other words, Triton is a bit of a bully and a bit of a rebel. Now, the good news for those of you who hate bullies is that Triton is not going to be around for, in terms of astronomical terms, not very long. In terms of human terms, it's going to be around for quite a long time. And so what's going to happen eventually is that it will slow down to the point of crashing back into Neptune, or become a beautiful ring around Neptune. So there's 2 possible choices for its future. Either become the ring, and that's when it reaches the Roche limit, which refers to essentially the ability of a moon or a planet to maintain its own spherical shape. If there's some kind of a gravitational force on the outside and it causes the planet to fall apart, it's called the Roche limit. It reaches that limit that causes the planet to fall apart. Now, but it's very likely that it's just going to kind of stop, and essentially what's going to happen is we can actually simulate this by using the powers here. Or we actually don't even have to use the powers, we can just go to actions and then click on 0 velocity, and this is what's very likely going to happen in about 3 to 4 billion years. It's just going to slow down until it crashes into Neptune and very likely disturbs a lot of other satellites that are orbiting around it. But the thing is, other satellites are so tiny compared to Triton. All of them together are not even close to being as big as Triton. And Triton itself is not very big, and here we go. That's the future of Triton. The big bully is gone, and so yeah, so the Triton itself is not actually very big. It's about 0.2 or basically 20 to 30% of the moon, our moon, and so oh, look at that, beautiful spots left. So yeah, it's not very large, but anyway, we're not going to be destroying any planets yet. And as you can see, actually, because it approached so close to Neptune, it actually changed the orbit of a lot of the other moons. So yeah, let's actually talk a little bit about the moons. This is what our main purpose is. But because there's actually only one major moon we can terraform, we really are going to be talking about the bully Triton. All of the other, here I'm going to pause this for a second. All of the other inner moons here, so these would be Naiad, Thalassa, Despina, Larissa, Galatea, and there's another one here, Proteus, which is actually relatively large as well, but not large enough to terraform. And there should be another one here that has a funny name. Maybe it hasn't been added to the game yet. There's another one that is referred to just by the number because it was recently found. Alright, I can't really find it anywhere. It's called S2004N1. It's essentially a nameless moon. But the thing about all of these little rocks here is that they're very similar in composition. They're mostly dirty snowballs. They're mostly anywhere between, what's the smallest one here? I think it's about maybe 20 kilometers. Let's find the smallest one. Who was it? And yeah, they're mostly between 33 kilometers in radius, and I think the biggest one, Larissa here, is 97 kilometers. And so they're not very large, they're not very prominent, they're not very massive, they don't really influence the either the tidal effects on Triton. They basically have no effect. They're just kind of big rocks, big enough to destroy the life on the planet, but not big enough to cause anything major in terms of gravitational shifts. Proteus here is a little bit bigger. It's about 200 kilometers, and it is a little bit more massive. But if you compare its mass to a mass of, let's just say, Earth, or no, that's actually not here, Moon. It's about 1,000 times, over 1,000 times lighter than the moon. So even Proteus here is not particularly exciting, but it is a relatively circular object. Now we don't really know if that's what it looks like because the picture we have to date is not particularly clear. And so yeah, this is Proteus's picture from Wikipedia, and this is the best picture that we have currently, and the only picture. It's from Voyager 2's trip, and it was actually, I think, taken somewhere in 1989. It doesn't actually say the year, the actual date, maybe possibly June 16th, but I think this is actually when it was discovered. And so yeah, it's a rock about 200 kilometers in radius, so this is about 400 kilometers in diameter. Not particularly exciting. It's basically a rock that has been accreted or created from the leftovers that were flying around, like all the rubble that was flying around Neptune 4 to 5,000, not 1,000, billion years ago, when Neptune was just being created. And essentially that is the biggest moon that is not Triton, but Triton is the one that we're going to be looking at in more detail. But let's actually look at some of the outer irregular moons here, and I'll just name them just for the sake of naming them. So right now we've talked about these moons, and these are actually called regular because they have a regular circular orbit, and a lot of them have a very specific pattern. So some of them actually orbit twice for every 3 orbits of the other moon. So there's quite a very kind of a patterned orbit because they've been doing this for so long. So they've actually acquired this particular pattern, and all of them are tidally locked, meaning that they are always facing with the same face to Neptune. Now this one is not behaving very well because I think in this game it's not well simulated, but it should be facing Neptune at all times. Then we have irregular moons, and the first one and the most important one is of course Triton. I don't know where it's gone. Where is Triton? It disappeared. Okay, I need to reload this. I think I did something with my Triton. Oh yes, that's right, we collapsed it into Neptune. I forgot about it. So yes, the most important one is Triton, which is right here. This is the biggest one and the most important one. And then we have a few other ones. So there is one called Nereid, which is about 170 kilometers in radius, slightly smaller than Proteus, but way smaller than Triton. So Nereid is right here, and it has a kind of a very interesting, quite eccentric, and not in the same plane orbit. So you can see it's kind of slow, it's very eccentric, and it's kind of obvious to astronomers that this was a captured object as well, very, very likely from the Kuiper's belt. And for an irregular satellite, for a regular moon, it's actually very large. Both Triton and Nereid are actually quite unusual, because usually the outer irregular satellites around planets like Uranus, Saturn, and Jupiter are very small. They're much, much smaller, much less massive than this. But these two are quite large, so kind of gives you an idea, or gives you a confirmation that these are very, very likely have been captured from Kuiper belt outside. So these are very similar to objects like Pluto, and a lot different from other regular satellites. And then we have 5 more irregular satellites with very, very strange or very large orbits that are so different and so in such a different plane from other satellites. So we have Sao right here. This one is about 22 kilometers in radius. There is Halimede right here, 31 kilometers. Neso, which is about 30 kilometers. We also have Samath, which is about 20 kilometers. And these are the irregular satellites that are... Oh, I missed one. And then there's Lomedea. Lomedea is also about 21 kilometers. And these are basically rocks that were also captured from the Kuiper's belt, but are a lot more like the irregular satellites of other gas giants. Now, the most important satellite, like I mentioned before, is of course Triton. Now, Triton is unusual in many, many ways, but specifically because it's so far away from the sun, it's actually one of the coldest objects in our solar system. Its temperature is, well, okay, it's not that cold. I think this game kind of exaggerates it a little bit, but it's approximately 38 Kelvin, which is about minus 230-ish degrees Celsius. And the surface of it is obviously covered in ices. This is all ice, but from what we understand is that it's not just water ice, it's things like methane as well. And interestingly, it also has quite a lot of frozen nitrogen on top of it. So nitrogen that is usually in the atmosphere, in the air, like on our planet. Our planet is mostly nitrogen. I think it's like 70% nitrogen in our atmosphere. This one here, the nitrogen basically froze because it's so cold here. It froze and it fell to the ground. So all this nitrogen ice can essentially be melted and turn into atmosphere. Now, this is one of the possibilities of how we could create a livable atmosphere here, is by basically melting this whole ice sheet on top of it. The other interesting fact about Triton is that it's also geologically active, so it does have a lot of things going on the inside, which causes the outside to change. So there's something called cryovolcanoes here, which are basically volcanic eruptions that are mostly ice, and there's also ice nitrogen geysers. Geysers are the water eruptions on our planet, but here will be nitrogen. And things like earthquakes, of course, because that's something that always comes with plate tectonics. And because of those eruptions, it has a kind of a small atmosphere. There's actually very, very thin atmosphere. It's not really well represented in this game, but it's something like 1/70,000th of the atmosphere on our planet. But you know, it's a start, so that means that one day we could actually possibly terraform this planet to be more livable, because it already has so much nitrogen. We just have to find and bring some oxygen to it, and that can be done by using all of this water that is flying around Neptune, you know, all of this ice, and essentially smack it into this planet. So let's actually switch to the other simulation here and start the terraforming process. I'm actually going to be using this right here called Solar Systems, All Planets and All Moons. If your computer is not powerful enough, you may not be able to simulate this very well, because if you look at this, every single planet, every single satellite is in this simulation. But usually what I like to do is hold control, select the ones I'm not actually dealing with, and then press delete to erase them. Just like this, including Earth, our home planet. I'm sorry, Earth, but you have to go. Even Mercury. Don't need Mercury. Jupiter is the one you really want to remove because it has the most satellites, so meaning that it does most of the slowdowns on your system. So we're going to just leave Neptune. Neptune, nothing else. and that obviously includes all of its beautiful satellites. So this is what it actually looks like as Neptune is flying, orbiting around the sun. So all of those beautiful satellites are orbiting around as well, except for Triton, who decided that he's going to go his own way and orbit against the flow. So I think it takes about 70 days. Oh no, sorry, I'm wrong. 45 days. 45 days to orbit Neptune. So every 45 days it passes by the same location in space. And because it's always facing Neptune, it's an tidal lock around Neptune. It's basically sort of rotates as it spins. So every 45 days you get 1 day on Triton. Now, to make this a little bit more realistic, we're also going to enable tidal heating here, because it's so close to Neptune, it does get a little bit of tidal heating effect. So it would basically cause the planet to heat up just a little bit more. But because it's tidally locked, this tidal heating effect is not very high. Planets that are not tidally locked, they usually get heated up so much that it's hypothesized that when Triton just arrived to this system and it wasn't tidally locked, it was so it experienced so much tidal effect from Neptune that it was most likely completely melted. It was most likely just a fireball for a very, very long time until it finally became tidally locked to Neptune. But here, if we actually go into temperature, we'll see that now we get a little bit of a radiative power from the tidal effect, meaning that we get a little bit more heat on this planet, and it's going to get a little bit warmer than it would be otherwise. And I'm sorry, I looked at the wrong thing. It's actually radiative power. Tidal power is not showing here. Is that because I didn't enable it enough? Or because it's already tidally locked? It's very possible that we might get no tidal heating at all. Let's find out. Let's see if this works. Yep, it worked. Alright, so there's a bit of tidal power right here, but quite a lot more, almost 10 times more radiative power from, that's power from the sun. But the thing is, because we're so far away from the sun, where's the sun? There it is. This is what it would look like if we were standing on the surface and we're looking... What is that? Did something just collapse into something else? Fragments. Uh-oh, something must have just smacked into something. I need to fix that. I did not expect that at all. But anyway, so this is what it looks like. This is the sun. And this is basically the night sky from Triton looking onto the sun. So it's a pretty beautiful view, actually. I'm going to accelerate just a little bit. Yeah, those fragments, those are not okay. What is that? Something totally just got destroyed. And that's something you might actually be headed this way and then collapsing into Triton. Okay, that's cool. Anyway, so yeah, that's the sun. It's very, very small. It doesn't provide enough heat. So most of the heat here will have to be provided by something else. And what is that something else? That's right, the greenhouse effect. That's what we're going to be aiming at. We're going to increase the greenhouse effect to the point where this planet becomes, or this moon becomes really, 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 really warm. Not hot, but warm, because right now it's really cold. Now, I'm going to actually, I think I need to reload this, because I lost something. I totally lost something. These fragments are from a collision with something else. Are they actually important to us? Yes, they are. Now, this is what Triton looks like compared to both the moon and Earth. So it's actually smaller than the moon. It's also less massive than the moon. It's a little bit more dense than other satellites, but it's way, way less dense than the Earth because it doesn't have enough iron in its core. But it does have a lot of interesting things on its surface. A lot of the atmosphere can be basically created on this moon by essentially just heating it up. The only problem is obviously keeping it there, preventing it from flying away into the outer atmosphere, because its gravitational acceleration on the surface is actually relatively low. It's even lower than the moon. But if we can actually figure this out by maybe introducing some really heavy gaseous elements that will, not fly away into space, then we might actually have a very, very successful atmosphere on it. But essentially, as long as you smack a bunch of comets into it, and not comets, asteroids, but if you can essentially heat up its surface, and we can do that right now by possibly smacking something into it. Let's actually combine it with, I know what we're going to do. Let's combine it with this beautiful body called Nerades. We're going to actually combine them together. So what I'm going to do is, I'm going to try to smack Nerade into Triton, and essentially they will become one. So a lot of the atmospheric surface ice will be melted when Narade smacks into Triton. It might be not very realistic because we don't really have technology to do it right now, but it might be possible in the future if you basically decelerate Narade enough to help it enter the lower atmosphere here. Or to make it even easier, let's actually just choose one of these objects right here, something that is relatively close in size to Narade. I think that will be Mimus. And basically what we're... Oh, I can choose now. Can I choose Narade? Yes, thank you very much. There you go, Narade. And we're just gonna smack Narade into Triton. But we have to make sure that we smack it just the right way because we don't want to change its orbit. So here we go. Okay, here we go. I'm gonna slow this down and we're gonna actually look at it as it approaches Triton as well. So here comes Narade. Oh. Huh? Alright, that was a little bit too fast. A little bit too fast. But, okay. I may have to correct its orbit now because I think it might have got misaligned a lot. And this is actually the problem with trying to... Oh wow. Yeah, it's actually going to escape Neptune. Trying to essentially collapse an asteroid, a very large asteroid, planetoid, literally planetoid, into another moon around a gas giant, because there's a high chance that will cause it to escape. And I think this is what's going to happen now. If I accelerate time, it's actually going to escape. Yeah, it's going to fly away from Neptune. So this was way too big. So definitely not Narade, because we just turned this into a star-like object. Although it's basically a molten terrestrial planet. And this is what Triton probably looked like when it just entered Neptune's orbit. So instead, let's try this again with a much smaller object. Let's actually just use Deimos. Deimos is one of the Mars's moons. So we're just gonna do that and slow down this to something more realistic. And here comes Deimos. Is that Deimos? There we go. Slowly going to approach Triton and smack into it. I can possibly accelerate this a little bit more. And this is actually a large enough object that it will cause a lot of the things on the surface to melt, but not a large enough object to cause any serious orbital change. And so this will essentially warm up the planet just a little bit, melt some of the ice on the surface, and we actually do have technology to change an orbit of an asteroid, a large asteroid, enough to smack it into a planet. It was actually one of the potential missions, future missions for NASA. Unfortunately, it most likely have been scrapped now because there's just not enough money or interest, but we do have the technology for it. So this would have warmed up some of the part of the planet. The shock waves and all of the heat will probably spread across the planet, warming up and melting the ice of nitrogen and carbon dioxide ice, causing it to escape and create some sort of atmosphere. Now we definitely have to do this a few times. We'll probably have to smack a lot of these things into our... Here, I'm gonna decelerate this a little bit. I'm gonna keep smacking things just because it looks pretty. So smack a lot of things into Neptune, sorry, not Neptune, Triton, giving it a little bit more temperature and also essentially melting the surface ice. This would obviously also add a little bit of mass, but not enough to make a difference. But what we're trying to do here is we're essentially just creating an atmospheric effect. We're trying to melt the ice and add a bit of atmosphere. Now, it doesn't really work that way in the game, so I do have to do this manually. I have to actually go in here and now start adding atmosphere. Now, specifically, we actually want to have a lot of atmosphere. We want to have approximately, I think when I tried this before, I had to have approximately 65 atmospheres of atmosphere. So that's 65 times the atmosphere of Earth. Now, some people before have actually commented, how can you survive in such a high atmosphere? Aren't you going to just, die and get squished and collapse into this little piece of nothingness because of the pressure? Well, not really. Let me just actually, I'm going to delete all fragments because they're causing a lot of slowdown for right now. So no, not really. The atmospheric pressure is not really dangerous for people, for humans. We can easily survive at high atmospheric pressures because we are mostly liquid. We mostly have liquid, and the air inside our lungs and inside our cavities can be pressurized, can be equalized by increasing the amount of air in those particular cavities. So this is what happens if you ever scuba dive. As you breathe the air, it actually increases the pressure inside your body and gets equalized. So you can go to really deep depths underwater, and I think the record up to date is about 370 or something over 300 meters. It's essentially 30 atmospheres, and the only reason the person had to stop was because he didn't have the right mixture of air. He didn't have the right air to breathe, and so if you don't have the right mixture of air, unfortunately you can die because oxygen becomes quite toxic at high pressure. And so that is something that we'll need to resolve in the future if we ever decide to settle on this planet. But anywho, so I've increased the atmospheric pressure, we've created this atmosphere now, and we now have, because of the atmosphere, the albedo here will most likely decrease to about 0.3. Albedo on this planet, on this moon, is actually relatively high, it's about 70 to 80%, but we will now decrease it to about 30 because that's what it would be like if we suddenly acquired atmosphere. And we're also going to add a little bit of water to it because it currently does not have any water on it, even though it does in real life. So we're going to add a little bit of water, and just for fun, a little bit of organics, maybe a little bit of hydrogen, and this will hopefully give it. Oh, here we go, ice. This is what I was looking for. Okay, that is a little bit too much. That is a little bit too much. Decrease it a little. I'm going to make sure that it has liquid water when it becomes a Terra-like planet. Alright, well, you know what? Maybe I can do it a little more. There we go. That's looking a little bit better. Here we go. Perfect. So let's just leave it at that. And now all we have to do is wait. So as soon as we have atmosphere, and this is a really thick, really pressurized atmosphere, we just have to wait, and we have to wait for a few years until the tidal effects and the barely visible sun warm up this moon and make it habitable. Now the thing is, we can accelerate this in the game. In real life we don't really know how it's going to work, but essentially what we're doing here is we're using the greenhouse effect that is here currently 238 degrees Celsius. In other words, the temperature will increase by 238 degrees due to the greenhouse effect. Now, on our planet, on Earth, it's about somewhere around 30 degrees. On planets like Venus, it's extreme, it's like 350-ish degrees. And so this is something that we need to start exploiting if we ever want to terraform outer regions of solar system. So I'm going to accelerate time now, and we're going to wait until this becomes a beautiful solar-like planet. I mean, I meant to say Terra-like planet, not solar-like planet, Terra-like planet. And here we go, at around minus 27 degrees, we start noticing clouds. So we now have clouds because a lot of the water started to, well, not just water, but other gases as well, started to evaporate and create a cloud-like surface on in the atmosphere. Now we just have to wait a little bit longer until the water starts melting, and all of this ice will convert into liquid water. And I think we just passed that threshold of 0 degrees Celsius. As you can see, the water started to become liquid. It's not very well visible though, because there's just not enough illumination from the sun. So this would be a very kind of a darkish world. Imagine living in constant dusk-like environment, sort of like what it looks like when it's evening, when the sun is on the horizon. It sort of gets to be kind of darkish. So especially for people that don't like the sunlight, the people that consider themselves vampires or basement dwellers, this would be actually a very good potential home. So this would be a darkish world that has one day lasts 45 days, and it's always kind of darkish, so there's just not enough sunlight. Do bring a lot of vitamin D if you decide to come here, because you're going to have trouble keeping up depression away. But other than that, that's it. This is the world that would be the world of the future where we can possibly live on. Let's actually look at the surface, see what it looks like. And here we go, look, this is the sky. This is what the sky looks like. Let's look at the sun, if I can find it here. Where is the sun? This is how small it is that I can't even see it. There it is, I found it. So this is what the sun would look like, And the atmosphere here would be very, very thick, so it would actually look a little bit more washed out. Imagine, it would be kind of similar to what atmosphere of Venus looks like. So the sun would be here very, very hardly visible. There would be a lot of clouds, a lot of really thick atmosphere. So it would be quite a dark place to live, but I'm sure by then we'll have technology to make this a very interesting world to live on and relatively bright as well. So, but definitely don't expect to see a lot of sun. And the fact that Neptune by itself has a very powerful magnetic field that protects a huge region around it from solar flares, we would be quite safe to live on this particular moon and enjoy a relatively relaxing and peaceful existence, because we would be protected from all those dangerous high energy flares that usually cause a lot of disruption on our planet, specifically on Earth. And to complete this video, let's observe this beautiful Neptune rise that is about to occur right now. Here we go. So this is a Neptune rise from Triton standing, in the water. And essentially this is what this would be like. And creating atmosphere on this planet would be not very difficult, but the problem is keeping it there, because the gravity here is so low. It's lower than on the moon. In other words, you can jump here relatively high as well. Keeping the atmosphere away from flying into the outer space is going to be a bit of a challenge. So we do need to create some really interesting gases that will be heavy enough to stay on the surface of Triton. All in all though, that is it. This is what Triton would look like if we were to terraform it, and this is how we could possibly do it. So this is a terraform Triton, and possibly one of the last terraforming videos of our solar system that I can think of. I'm going to try to terraform Pluto and a few other less known bodies in the future videos, specifically things like Ceres, which is another planet-like body that orbits between Jupiter and Mars. But in terms of terraforming actual objects that that scientists have thought about terraforming, I think we're done here. This is the last one, Triton. Anywho, this has been What the Math with Universe Sandbox 2 and terraforming the only moon of Neptune that is really worth terraforming. Now, I'm also posting the link for this particular game in the description below, because a lot of people have been having trouble finding where to buy it. So this game is available for purchase, even though it's still alpha. Now, alpha 15 is coming out very, very soon. I'm really excited because there's a lot of changes that are coming, and as soon as it comes out, we're gonna take a look at it as well. Anyway, thank you guys, and game you later. Bye bye.